Since we've talked about physical properties of chiral compounds, next we're going to talk about chemical properties, and we'll see how reactions affect chirality and how chirality affects reactions. First, let's take a look at an example of a reaction that creates a chirality center. So looking at this molecule, we don't have any chirality centers, but looking at this product, this carbon is a chirality center because it's connected to an OH, a methyl, an ethyl, and a benzene ring. So this is a reaction that creates a chirality center. This is a reaction that we'll be looking at later this year, so you're not responsible for the details yet. I just want to point out what's happening. This is called a Grignard reagent, and it's a source of a nucleophilic carbon. So we can think about CH3 as our nucleophile. In particular, we can think of it like this, where this nucleophile shares its electrons with this carbon, pushing these electrons up onto the oxygen, forming a new bond between the carbon and what used to be the carbonyl carbon. So this is that new bond. What was a double bond became a single bond, and then this O- is going to grab off a proton, resulting in the formation of this alcohol. So let's think about when this nucleophile adds, this carbon is sp2 hybridized, which means the shape around it is trigonal planar. So the methyl group can come in from the front face. So let's say it's coming in from in front of the screen. That would push the oxygen back, and this group would be in the front. But it is also possible that the nucleophile can attack from the back face. So let's imagine that this is attacking from behind the screen. Well, that would lead to the OH being pushed forward, and the methyl would be coming in from the back. So it's equally likely that the nucleophile would add from the front or from the back. So what you're going to get is a 50-50 mixture of a pair of enantiomers. Throughout the year, we're going to see many examples where optically inactive starting materials lead to optically inactive products. Our starting materials are optically inactive because they are both achiral. Our product, we have made two optically active compounds, but we made them as a racemic mixture. A racemic mixture overall will be optically inactive. So we're going to see this multiple times where with reactions that create a chirality center, we will make a mixture of enantiomers. What about reactions that occur at a chirality center? So here we have a chirality center, and here we have a chirality center. This is a reaction we'll be looking at later this semester, and overall it's a substitution. So the OH is replacing or substituting for the bromide. And so the carbon-bromine bond no longer exists. We have a new carbon-oxygen bond. The same thing happens down here. The carbon-bromine bond no longer exists. We now have a new carbon-oxygen bond. Well, when a reaction occurs at a chirality center, we have a few options. We can have retention of configuration, or we could have inversion of configuration. These would be the options when we have a substitution at a chirality center, for example. Which one is going to happen depends on the mechanism of the reaction. And so we're going to talk about this in detail. This reaction proceeds in one step, and the nucleophile adds from the opposite face, leading to inversion of configuration. And so from this chiral starting material, we will get this chiral product. But this reaction proceeds by a different mechanism. We are going to get some products that result from inversion of configuration, similar to what we saw above, but we will see some products that result from retention of configuration. So here our groups are in the same relative orientation as the groups here. So this introduces a new term, relative configuration, in contrast to absolute configuration. So absolute configuration, this is what's given by R or S, determined using the Conning-Gold-Prelog priority rules. Relative configuration refers to compounds that have similar groups occupying the same location in space. So here we have a propyl group, methyl back, ethyl forward, bromine to the right and in the plane, OH to the right and in the plane. So these have the same relative configuration. Whether they have the same absolute configuration depends on priorities, but we're talking about different things. This one we could determine whether it's R or S based on looking at the structure. This one we can determine whether it's R or S, but comparing this structure with this structure, we can see that they have the same relative configuration. This one compared to this one has the opposite relative configuration. So when a reaction occurs with retention of configuration, the starting material and the product have the same relative configuration. When a reaction occurs with inversion of configuration, then the starting material and product have the opposite relative configuration. Whether we have R or S, whether that is maintained or changed in a reaction depends on the particular reaction. And just to make a connection with the previous slide, here we are starting out with an optically active starting material, and we will end with an optically active product because of the particular mechanism of this reaction. In the second example, we are starting out with an optically active starting material. We're going to make a mixture of products. If we make exactly 50-50, then we're going to end up with a racemic mixture, which would be optically inactive. If we don't have a 50-50 mixture, maybe we get 60-40, then we're going to have partial racemization. So we're partially making a racemic mixture. These are all things that you're not responsible for right now, but these are things that we need to be on the lookout for when we start talking about reactions in depth. Next, let's look at a couple of reactions that do not affect a chirality center. So in our first example, this is a chirality center, and the reaction that's happening is substituting an OH for a bromine. We still have this chirality center, and no bond is being formed or broken to the chirality center, and so the orientation in space will be maintained. So for example, if we start out, let's say we have our ethyl group, here is our CH2OH, maybe our methyl group is forward and our hydrogen is back. And when this undergoes reaction with HBr, we are going to get this product. This has changed from an OH to a Br, so we broke a carbon-oxygen bond, we formed a carbon-bromine bond, but no bonds were broken to the chirality center, and so this will have the same relative configuration. It still has the same groups in the same orientation. So if a reaction does not occur at a chirality center, then the relative orientation at that chirality center will be maintained. In our next example, here's a chirality center, here is a chirality center. This reaction is called a hydrogenation. Notice we have an alkene in our starting material. Hydrogen and palladium, this is going to add hydrogen across the double bond so that we get an alkane. Once again, no bond to the chirality center changes. So if we were to start out with, let's see, here's our propyl group, carbon, here is our alkene, and maybe we have our OH forward, H back. When we carry out this reaction, we will have our propyl group. This is now a CH2CH3. Here is an OH and an H. So no bond changed to the chirality center, so we have the same orientation. In other words, we have the same relative configuration. But let's assign RS configuration, so absolute configuration. We have our oxygen has highest priority. Now here we have, let me come up here, this carbon compared to this carbon. This is connected to a carbon, hydrogen, hydrogen. This is connected to carbon, carbon, hydrogen. So this will have priority 2, 3, and 4. Now our lowest priority is back, so we focus on priority 1 to 2 to 3, and this is going counterclockwise, so this has the S configuration. In our product, the oxygen is still priority 1 and the hydrogen is still priority 4, but let's look up here. This carbon is connected to HHC. This carbon is connected to HHC. Remember back here, because it was a double bond, it counted as HCC, but now it's HHC. So then we move out another carbon. This carbon's connected to HHH. This carbon is connected to HHC. And so this group has higher priority than this group. So this is priority 2, this is priority 3. Our lowest priority is still back, so as we trace priority 1 to 2 to 3, now we are going clockwise, and so this is R. So because no reaction occurred at the chirality center, our starting material and our product have the same relative configuration. But because the priorities changed, they now have a different absolute configuration. So there's a lot to consider as we start working on reactions. Now here we have one more example, and this is a situation where we might have reactions that are affected by a chirality center. So here again, we're looking at catalytic hydrogenation. We have an alkene. When it's treated with hydrogen and palladium, this is going to add hydrogen across the double bond, and both hydrogens add to the same face. If they add to the front, then we get the hydrogens in front and the methyl group in back. But they could also add to the back, which would give the methyl groups forward and the hydrogens back. So these are actually the same compound. We could pick up this one, flip it over this way, and it's the same thing. But I just want you to picture how hydrogens can add to the front face, or they could add to the back face. Now, in this molecule, we have a chirality center. This chirality center is not changed in the reaction, but it is going to change the reaction a little bit. So once again, the hydrogens could add to the front, and that would give this, where hydrogens are in front and the methyls are in back, and our T-butyl group is in front, or the hydrogens could add to the back. So this is in front. If the hydrogens add to the back, that pushes the methyl groups forward, and we get this. So in this case, it makes a difference whether the hydrogens add to the front face or to the back face, because these are stereoisomers that are produced. The same connectivity, different orientation in space, and they cannot be interconverted. In the first example, it's a 50-50 chance that hydrogens would add to the front face or to the back face. But in this case, it makes a difference because this bulky T-butyl group is going to get in the way. And so it actually prevents the hydrogens adding from the front face, And so we will end up with more of this where the hydrogens add to the back face. So, although the reaction doesn't occur at the chirality center, sometimes the chirality center will influence the outcome of the reaction. So the details of reactions and chirality are not something that you're responsible for right now. I want you to start thinking about this, and I want you to pay attention to the stereochemical outcomes when we start talking about reactions. For now, I just want you to be aware of these different possibilities where a reaction creates a chirality center, a reaction occurs at a chirality center, a reaction occurs not at a chirality center, but it does or does not have an effect.